All right, strap in, because today we are diving into an algorithm that is literally making waves.
Literally.
We're talking about turning chaos into, get this, cosine waves.
Yeah, it's pretty wild. It's a fascinating study in how something predictable can emerge from randomness.
Right, like if you can picture a giant Galton board, that pachinko-like thing,
Right.
you drop a ball, it bounces around randomly, and yet,
Yeah, they all end up forming that perfect bell curve at the bottom.
exactly, this algorithm is similar, but instead of a bell curve, it creates this repeating wave pattern.
Yeah.
And we've got the research paper, code snippets, actual results data.
Oh, wow, the data's there.
Oh yeah, we're going deep on this one.
Awesome. Yeah, that's great.
So let's unpack it.
Yeah, what's fascinating is that the algorithm itself is surprisingly simple. It all starts with simulating these random walks.
Okay, so like those digital choose-your-own-adventure books, but instead of turning pages, our little code balls are bouncing around.
You got it. And just like with the Galton board, we need to keep track of where they land.
Yeah.
That's where these bins come in. So each bin represents a point on our digital board.
Got it.
Okay.
So we've got our digital balls bouncing around, landing in bins.
Yeah.
But how do we go from that to like a smooth wave?
Yeah.
This is the part where my brain usually checks out.
Yeah, this is where the algorithm gets really clever.
Okay.
It uses a bit of math wizardry, specifically something called the modulo operation and these scaling factors.
Okay, hold on.
Yeah,
That sounds scary.
they sound a lot scarier than they are.
Can we get the explain it like I'm 5 version?
Absolutely. Think of the modulo operation like a clock face, right?
Right.
So if you go 13 hours past 1 o'clock, you don't go to 14 o'clock.
Right.
You go back to 2 o'clock.
It wraps around.
Exactly. It wraps around.
Okay.
And so this wrapping, combined with, some clever scaling, takes the randomness of the balls landing in bins and transforms it into points along a cosine wave.
Wait, so by wrapping the results around, we're essentially like shaping the chaos into a wave.
Precisely.
Wow.
And what's even cooler is that the research team provided updated Python code.
Thank-
So this isn't just theoretical. This is up and running.
Oh, I love that. I love it when we have actual code because that means someone out there is actually doing this, making these waves.
Right.
But why?
It's amazing.
Why is this so groundbreaking?
Yeah.
What's the so what here?
What's really cool about this algorithm is that it challenges how we think about complexity.
Okay.
We have the code, right? So we know the rules of the game, but predicting the exact shape of that wave, that's a whole other story.
You're saying we can't just plug in a few numbers and know what the wave will look like ahead of time?
Exactly.
All right.
That's because of something called computational irreducibility. Think of it like
Okay.
our Galton board again. So imagine you've got this perfect Galton board,
Okay.
right? And you know everything about it, the spacing of the pegs, the weight of the ball, like everything.
Okay.
You drop a single ball, can you predict exactly where it will land?
No way. It's bouncing all over the place.
Right. You can only know for sure after you run the experiment, right?
Right.
You have to let the whole process play out, even with perfect knowledge of the system.
Okay.
We can't shortcut the process.
So even though we have the code, running the algorithm is kind of like running an experiment.
Exactly. And, that has huge implications,
Okay.
especially when we think about complex systems in the real world.
Okay.
Take weather forecasting, for example.
Yeah.
Meteorologists use these supercomputers, tons of data,
Right.
but predicting the weather beyond a certain point is still really hard.
Yeah. And I'm constantly refreshing my weather app to see if the forecast changed again.
Exactly.
So this idea, computational irreducibility, it helps explain why it's so hard to predict things like the weather, even with all the computing power we have.
Exactly. And it's not just the weather. It applies to things like economics, stock markets, even things like traffic patterns.
Oh, no.
These systems have so many moving parts that their long-term behavior can be really unpredictable.
Okay, so we've got this algorithm that makes waves from chaos, and it teaches us about the limits of prediction, even with the code right in front of us.
Right.
But we also have the actual results from running the code.
Yeah.
What did they find when they actually let this thing loose?
Well, they ran the simulation for 70 cycles, and they focused on the amplitude of the wave, which basically means how high the peaks of the waves were.
Okay.
And that's where it gets even more interesting.
Hit me with it.
Yeah.
Did it match what they were expecting?
So they had a formula to predict the amplitude
Okay.
based on the algorithm settings.
Uh-huh.
But when they compared that to the actual amplitudes they got from running the code,
There was a difference.
yeah.
Like, the code was a rebel, and went off script.
Exactly. The actual wave amplitudes were noticeably higher than the formula predicted, especially as they ran more cycles.
Okay, so the code is creating these beautifully ordered waves from chaos, but it's not behaving exactly how the math predicted. This feels like a plot twist.
It's like math can only take you so far, right? And then reality kind of steps in and says, I'm going to do my own thing.
Looks like the code has a mind of its
A
own.
little bit, yeah. It's exciting, though, isn't it? It means there's more to discover here.
Absolutely. And that's where we'll pick up in part 2 of this deep dive. We'll dig into these unexpected results and explore what they might mean. Don't touch that dial. We'll be right back. So the code is like, hey, math, appreciate the guidelines,
Right.
but I'm gonna add my own flair.
Yeah.
I kind of love that.
It's really neat.
Does the research explain like why the actual results were different?
That's the really intriguing part. They left that open for further investigation.
Oh,
They handed us this amazing tool and said, all right, go explore.
I like it.
And one of the most exciting things is that this algorithm has adjustable parameters.
Okay, so like settings you can tweak.
Exactly.
What happens when you start playing with those?
That's where things get really interesting.
Okay.
Right? Remember how the algorithm creates those cosine waves?
Right.
Adjusting the parameters can change that.
Okay.
We might get different patterns, maybe even something totally unexpected.
Hold on. So we could get completely different patterns, not just different looking cosine waves.
Yeah.
Just by tweaking a few things.
It highlights how even a slight change in a complex system can lead to dramatically different outcomes.
That's kind of mind-blowing. Like
Yeah.
I'm thinking about like
It's really quite amazing.
baking bread.
Yeah.
Change the amount of yeast, the kneading time, even the oven temperature.
Totally different loaf.
You get a completely different loaf.
It's true.
Okay, now I'm really understanding the power of this thing.
Yeah.
It's not just about these cosine waves. It's about what else is possible, what other patterns are hiding in there.
And that's what I find so exciting about this.
Yeah.
This research opens up a whole new avenue for exploring complexity and randomness.
Okay.
It's like they've handed us a map, but large parts of it are still uncharted.
So they're basically inviting us, the listeners, to do our own exploring. To go out there, tweak those parameters, and see what hidden patterns we can unearth from a little bit of digital chaos.
I love it.
I don't know about you, but I'm feeling inspired.
As you should. Sometimes the most groundbreaking discoveries come from those who are brave enough to venture off the beaten path,
Right.
to ask, what if, and see where the answer takes them.
So it's kind of like they gave us this really cool toy.
Yeah.
You're like, go figure it out, see what it can do.
Exactly.
It's awesome.
Yeah, and who knows, right?
Right.
Maybe one day we'll be back here on the deep dive,
Yeah.
unpacking your groundbreaking discoveries.
You'd love it.
Because you took this idea
Yeah.
and you ran with it.
Right. So we dove into this algorithm that makes waves from chaos.
Literally.
We learned about computational irreducibility, the limits of prediction,
Absolutely.
and the beauty of unexpected results.
It's all there.
Which is kind of a theme of this show, really.
I think so, yeah. Embracing the unexpected.
Yeah, that's where the cool stuff happens, right?
Absolutely.
So until next time, keep diving deep, keep exploring, and who knows what you'll find.
Happy exploring.